Hello, and welcome to this recording, which will introduce you to Sherlock, a reliability physics analysis tool provided by Ansys. Sherlock enables organizations to investigate potential reliability issues and make a lifetime prediction for printed circuit board assemblies. This is one part of a series of short recordings which will present and demonstrate different aspects of where and how Sherlock can be used to analyze your PCB reliability through the design flow. In this recording, we will look at how to use Sherlock early in the design phase. Initially, let me provide a brief overview of what Sherlock is. Ansys Sherlock addresses the question of printed circuit board reliability upfront during design. The goal is to reduce or even remove expensive PCB test iterations by addressing the potential issues before physical prototype, and further to ensure and enhance the reliability of your PCB product for its projected lifetime of operation in the field. Sherlock uses a combination of physics equations, finite element analysis, and materials knowledge to provide this reliability calculation. Just to be clear, Sherlock only looks at the mechanical shock, vibration, and thermal risk to the PCB assembly, that is, the components, the modules, the board, and the solder joints connecting them. Sherlock builds on the information produced by the electronics computer-aided design tools and, through simulation, considers the physical environment in which the design will operate, and thereby creates a time to failure or reliability prediction for your PCB assembly. This enables designers to make decisions early in the design process that can reduce those test cycles, reduce time to market, and impact the warranty costs. Sherlock provides most value when implemented in the early design stages. So, for electronics engineers looking at the initial part selection for identified functional blocks, there'll be a handful of key components, and these can be input into Sherlock to run quick tests and work out any physical component mismatches. Essentially, this is running a quick coefficient of thermal expansion check on the components, providing a yes/no recommendation for suitability. You can also carry out some basic what-if analysis on the results that Sherlock feeds back, which can affect reliability, for example. If the component is available in different package styles, such as plastic or ceramic, you can determine any improvement. Or perhaps you could investigate if you were to use a larger than normal recommended pad size for a component. Sherlock enables these simple investigations to be carried out quickly, and based on these results, you can filter whichever way you want: cost, availability, manufacturability, and so on. At this early stage, it's all about avoiding costly errors later in the process. Let's have a look at how this would work in practice with a short demonstration from my colleague.
Once we have selected our parts we want to use on our board, it takes us just 5 steps to gain deep insight into the reliability of these components. We just have to import our parts list, add further parts information, apply standardized thermal cycles, run the reliability analysis, and finally check the reliability results. To begin with, we import our initial part selection into Ansys Sherlock. All the columns from our Excel file are mapped into the parts list. Sherlock now automatically lists all our components. In the next step, we need to add additional information like sizes and materials to our parts. With our inbuilt Sherlock parts library, we can check if these components were used before and simply reuse this data. In this case, we successfully updated all parts with the missing information. Once we see our parts marked in green, we can trust that we are using the right information and we are getting the right results in the end. The last missing information is about the PCB board itself. Sherlock automatically creates a default board stackup which contains all the material data. Of course, we can change this to get an even better representation of our board. The only thing missing for running our analysis successfully is a thermal load case. At this early stage, we make use of standardized load cases. We simply load our life cycle definition. All the information of the cycle duration and the temperatures are now available. Everything is in place and we can run our analysis. All we have to do is select the thermal cycles we are interested in and hit the run button. Sherlock now automatically builds the mathematical model and solves all the equations. We can proceed to our final step and check the results. Sherlock already post-processed the results in various predefined result views. I start with checking the live prediction curve. In the lower left corner, we can see our reliability goal of 4 years of service with only a probability of failure of 3%. As we can see, we did not reach our goal with these initially selected parts. After only about 2 years, we see a higher probability of failure. To learn more about the critical components, I switched to a tabular view. Here you can see all the parts listed. Some of them are red. This means high risk of solder joint fatigue failure. We can easily see that these risky parts are 4 ICs and a couple of resistors. Others are yellow. We should keep an eye on them. But most parts are fine and we don't have to worry. Now we have seen all the 5 steps and gained deep insight into the reliability of our initially selected parts. It's an easy task to improve the reliability of our critical parts. Let us start with the 4 failing ICs. Of course, we can change the package type. This means extra cost, what I want to avoid. Better cooling could also be a solution. I keep that in mind when I position these parts on the board and place them at the outer edges. That should lead to a better cooling and therefore better reliability. Regarding our failing resistors, increasing the pad size could be a good solution. I simply added the parts properties and changed the pad dimensions for these parts. Now I just rerun the solder fatigue analysis with the same settings as before and wait a few seconds. In the updated results, we can see that our resistors are more reliable. Changing the pad size was a good idea. With Sherlock, it was easily possible to check the reliability of our initial part selection. With just a few mouse clicks, we changed some of our settings and improved the performance of our board.
So, in summary, we have shown how you can use limited data just from an Excel parts list to assess potential reliability issues and the compatibility between projected components on a PCB. Decisions can be made early on for component type and material selection. No detailed knowledge of mechanical analysis is required, which means this can be used by electronics engineers, PCB engineers, thermal engineers, or indeed any on the project team. Watch our next video to see how you can further use Sherlock to address your PCB assembly reliability ahead of prototype. Thank you for watching.